You know, we usually hear the quote, "Those who can't remember the past are condemned to repeat it," in a history class. But what if I told you that this is actually the absolute ultimate secret to writing lightning-fast computer code? Right? When we talk about coding algorithms, we almost always just think about math and logic. But today, we're going to reframe coding. It's not just math, it's about memory. Because when your code can actually remember the past, well, it stops doing the exact same exhausting work over and over again.
Welcome to this explainer. Today, we are demystifying dynamic programming, or DP for short. Now, I know what you're thinking. This is notoriously one of the most dreaded topics in literally any algorithms class or technical interview. It strikes fear into the hearts of coders everywhere. But listen, we're going to transform this totally intimidating subject into your new intuitive superpower. We'll break down these complex theories into really clear, highly logical steps. And by the end of our time together today, you'll see that it's way less about complex mathematics and honestly a lot more about simple, strategic record keeping. So, here's our roadmap for today to get your brain geared up for this. First, we'll cover remembering to avoid repeating. Then, we'll look at the top-down versus bottom-up approaches. Next, we'll compare tabulation and memoization. After that, we're conquering some classic DP problems. And finally, we'll wrap up by mastering the overarching DP pattern. Let's dive right in.
All right, Section 1, Remembering to Avoid Repeating, the core idea.
Before we get completely lost in massive code blocks and complex arrays, we really need to define what dynamic programming actually is at its absolute foundation. And you know what? The overarching idea is incredibly simple. Dynamic programming is just saving the result of a solved problem with a particular input for future reference. That is literally it. Think about it. If you've already spent the computational power to solve a specific subproblem, just save the answer, cache it, store it in a table. Whatever you do, just don't waste time solving it again later when the exact same question pops up. It's basically the ultimate form of computational recycling.
Moving on to Section 2, top-down versus bottom-up, the two paths. Once you actually decide you want your program to remember its past, well, there's a bit of a great divide in how you implement that memory. There are two distinct mental models for attacking these problems. Our source material brilliantly illustrates this difference using a really relatable metaphor about learning. Check out version 1. Study the theory first, accumulate that basic knowledge, and build your way up to mastering the classic problems. That is a classic bottom-up approach. Now, contrast that with version 2. Jump straight into the super complex DP problems right away, break them down as you go, and realize the underlying concepts to master it. That perfectly describes top-down logic. They both get you to the exact same destination, but the direction of your learning, or, in a computer's case, its computation is totally reversed.
This brings us to Section 3, Tabulation and Memoization Compared. These are your tools.
So these are the two primary weapons in our algorithm hero's journey. First up, we have tabulation, which maps perfectly to that bottom-up approach we just talked about. You start at the absolute simplest, most trivial base state, what we call DP0. From there, you just follow state transitions sequentially. You solve the next slightly harder problem, then the next, accumulating answers as you sequentially fill out a table. You are literally building the solution from the ground up. And the beauty of this is that it mathematically guarantees that any subproblem you might possibly need has already been solved and recorded by the time you reach your massive destination state at DPN.
And then we have memoization. This is the top-down optimization. Instead of starting at 0, you start right at the massive destination state, DPN. You look at it and say, okay, I don't know the answer to this whole thing, but I can break it down into smaller subproblems recursively. You dive deeper and deeper until you finally hit a base case. And here's the magic. As you climb back up, you store every single result in a cache memory. If you ever ask the program for that exact same subproblem again, it completely skips the math and just pulls the previously computed answer directly from the cache.
It's really cool to see how cleanly these structural differences contrast. Tabulation starts at the base state and populates via sequential table filling. Memoization, on the other hand, starts at the destination state and populates via recursive cache filling. Now, generally speaking, tabulation is faster in execution because it totally avoids the overhead of recursive call stacks. But memoization can sometimes be a lot more intuitive to write because you're just naturally tracing the logic of the problem straight downward. Section 4. Conquering Classic DP Problems. Welcome to the battleground.
Okay, theory is great, but it's time to test our new weapons against real-world boss problems from LeetCode. So ask yourself this. In an array of numbers, when is a negative number actually worth keeping?
This introduces a really famous challenge called the maximum subarray problem, along with a brilliant solution known as Kadane's algorithm. To really wrap our heads around it, we need to shift our perspective and start thinking about arrays as consecutive combo chains, kind of like you're playing a video game.
Let's completely gamify this, specifically looking at the maximum product subarray variation. Positive numbers, they're your friends. They build your combo chain multipliers higher and higher. Zeros are brutal. They're the ultimate combo breaker that instantly resets your hard-earned chain to 0. But negative numbers, well, they're tricky. A single negative number acts like a poison. It instantly turns your massive positive high score into a massive negative number. But what happens if you encounter a second negative number? Boom! That second negative acts as an antidote. A negative times a negative becomes a massive positive again, totally saving a poisoned combo chain. And this is exactly why our algorithm has to simultaneously track both the maximum positive state and the minimum negative state.
So the absolutely crucial point here is how we handle this greedy-like intuition. Kadane's algorithm tells us to keep a running count of our current subarray. We are constantly updating our maximum found so far, but the very second our running subarray sum drops below 0, it becomes dead weight. It just isn't worth keeping because any future number added to a negative base is just going to be dragged down. So what do? We ruthlessly throw the negative baggage away and reset our running count back to 0. And honestly, this brilliantly illustrates the sheer raw power of dynamic programming. A naive brute force approach to checking every possible subarray combination, that's going to result in a sluggish, painful cubic runtime. But by simply remembering our running totals and resetting strategically, our hero slashes the runtime down to a lightning-fast linear time, O of n. We literally just sweep through the array exactly once.
Let's see how this builds into another classic boss battle, the coin change problem. You're given denominations of coins and a target amount to make. Notice how we break this into an optimal substructure. We define f of a as the minimum coins needed for amount a. We don't try to guess the whole massive combination at once. Instead, for any given amount, we just subtract the value of a coin we already have, look up the previously saved answer for that new smaller amount, and just add 1 for the coin we just used. We iterate this bottom up, starting all the way from 0 right up to our target amount.
Which brings us to our final part, Section 5, Mastering the DP Pattern, the Resolution.
We've slain the bosses, and now it's time to summarize the fundamental patterns we've learned so that you can easily recognize them out in the wild. No matter how intimidating a dynamic programming problem looks at first glance, it almost always boils down to this repeatable, universal template. Step 1. Define the base cases where the answer is absolutely obvious, like, knowing that an amount of 0 requires 0 coins. Step 2. Develop a strategy to compute the complex cases strictly from simpler ones, like adding 1 coin to a previously calculated amount. And step 3. Link your final answer back to those base cases using either a bottom-up table or a top-down recursive cache.
And that brings us to the end of our explainer. See, dynamic programming isn't magic, and it certainly isn't an impossible math test designed to ruin your day. It is simply the discipline of taking a massive, scary problem, breaking it down, and vigilantly writing down your answers so you never have to repeat your own hard work. Now that you hold the power of memory, and you actually know how to wield tabulation and memoization, which impossible problem will you optimize next?